I now remember. Yeah, and so the goal here is to just to get used to this notion of factors of a polynomial, right? So factorization in polynomials, and so that we can use this to understand the concept of GCD of polynomials, okay, and then use it to prove the Bezout theorem. We will the similar, the ax plus by equal to 1 has solutions, that kind of thing for polynomials. And that's one goal. And then there is another thing which we had picked up, which I'll talk about. So yeah, but here factorization of polynomials had given a problem. But before I just state the problem, let me say that, well, factorizing a polynomial just means to write a polynomial as a product of two other polynomials, right? I mean, all of us know that, obviously. One very rather special case, and maybe most very important case, or rather the best possible case in some sense, is when you can completely factorize, right? Completely factorize would mean, for example, if I give you, let's say if I give you this. So can you just tell me what factorization of this is? Oh, am I not sharing the screen? Can others see the screen? I think. So yes, just do that and you should be able to see the screen. Yes, and Pragadish, sorry, can you just send me your mail ID? Maybe you can just, yeah, now here you can send, or what if you want. While he just, okay. Perfect. So this is just simple, just this factorization. Okay, how about factorizing this one, maybe? Anyone who wants to try? So please try to factorize this. Good. Okay. So there are several cues using which you can factorize this, right? Not going into that. The point is that you can check that this is the correct answer. Yeah. We have discussed in the past what are the cues to factorize this kind of thing. Like you could check for the integer factors, and fortunately it works. Like one, what are the factors of 6? Those are your possibility. Those are your possible candidates for the for your integer factors. They may not necessarily work, but yeah, you can work it out and you can see this is a factor. So why do I say this is a special case, best possible case? Because in this case, we are getting a complete factorization, right? Do you see? So again, the goal here today is to get used to this notion of factorization, right? Because it's not just about knowing that it's a product of two polynomials. That's not enough, right? This is complete factorization. Would anybody want to say why the word complete here is a good word, if you think it is? Okay, we are not getting the values in the sense we are getting the roots. We are getting the values for which it becomes 0. That's right. That's right. Yeah. Yeah. That is why it's a good thing. So in this case, we are able to completely factorize, okay, in the sense that you can no longer factorize it certainly, right? Because the factors are linear. So in any way you want to understand it, the linear factors, or you're getting the roots that way. Okay, so if you know the roots, then also you know the linear factors. But the point that we're trying to understand is you may not always be able to completely factorize a polynomial. You may not always need to completely factorize a polynomial. Okay, and if you restrict what numbers you are using to factorize, then you may not be able to completely factorize. For example, if you only want to use rational numbers, then this cannot be factorized because this can be factorized using root 2. But in your certain context, root 2 may be a useless number, right? If it has to be an integer for certain context, then root 2 is useless. In that case, that is not factorizable. Okay. So the point that I'm trying to make here is that sometimes we may not be able to do complete factorization, and that gives rise to more kinds of other kinds of factors which you will not be able to directly notice from the roots. Like these factors you can directly notice from the roots, right? I'm sure if some of you won't have to just factorize this, just you would have to check the roots. Like you would say, okay, one is a root, yeah, so x minus 1 is a factor, good. So you're finding the factors from the roots, but not always that can be done, and not always is the best thing to do. Okay, so that's why we are going into taking a dive into a little bit of other kinds of factorizations, non-complete factorization. Okay, so but I would try to do that via a problem, a number theory problem. Okay, and I think that I mentioned this last time. So I don't remember the exact example, but it was something to the power, any power, the power doesn't matter. Okay, it does matter a bit, but yeah, just maybe keep it as 4. And then I would like to maybe, yeah, let's just start with something, then we can see. Sorry, yeah, so this is maybe if I give 7, yeah. Let's try, then we can understand if it's okay. So is this number a prime? So I had asked this type of question last time, and obviously for some kinds of numbers, I think, for example, we Ishana, I think, had given us some different argument using the last modulo 10 last digit thing. Sometimes that can be good enough, but in general, I had given an approach which you could use. Let's see. So are there any ideas? So I had asked this question last time and I suggested something. Have you? Yes, right? Because then it's a general thing that you try to factorize. Yes. So you should try to consider x to the 100 plus 4 and try to factorize this. Any ideas? No? Okay. So let's try to make it a little simpler. Now, are there any ideas? So can you factorize x to the 4 plus 4? Let's say I told you that there is a way to factorize it. Can you factorize it? No? So nobody knows how to factorize this. Okay. So how about one hint? Maybe you can think about try to write it like this. So this is just so this factorization that we will be doing today is a very standard factorization and it's going to be useful in many places. I'll give the name of it. It's called so this is I think called and you'll find it in several books and several places online. It has very many applications. So I think it's this only German identity or something it's called. Sophie German identity. It's useful in many places. But let's just work out and see that it is just a factorization trick. So if it was a difference, then it was, so I mean, let me ask this. So, I mean, if this was this, then could you factorize? Can anybody factorize the latter one? Okay, good. So, but can you just tell, or anyone can, okay, so then you don't say this. Can anybody say the latter one? Um, x square. Yes, right. Yeah, so that would be, yeah, it's square of x square. Yeah. Right. That's what you said. X square plus 2, x square minus 2. That's good. So that's easy to factorize. But when it comes to the plus, then usually it's not factorizable. Okay. But in this case, so let's see what Ishana has done. So yeah, Ishana, you can tell. Or you also factorized. Okay. So has anybody else also factorized it? No. So let's see. So let's Ishana, you say because you did it, said it first. No. So this you wrote and then, but okay. X square plus 2 whole square right, right, right. Okay. So you're saying this is the same thing. Yes. So that's what you, so you have completed the square. That's right. No, that's right. That is precisely what I was also, that means is this is the, yeah, that's correct. And yeah, so basically to complete the square, one can just think about this, and then you have to subtract this, same thing. And this is motivated by, I mean, as I would just say, is to complete the square. And this is what you end up with. But it turns out that this again becomes the difference of squares, and that's because of this 4. 4 is the special number right here, which makes this work. Yeah. So this is the thing. Yes, Aparna, your solution, is it? It's the same. Ah, good. So basically, so that's all good, very good. So, but in the end, the best thing is that we have this nice factorization. That's yeah, easy, elementary, right? There's nothing to it. It's a coincidence to some extent, right? Because this is usually not factorizable, this kind of thing. Okay, if you say x to the 4 um plus y to the or let's say x to the 4 plus 8 or 16, this you cannot factorize. Okay, but I'm not asking you to prove that. Okay, you can, it's slightly difficult to prove. So something you cannot factorize, something is a little, yeah, but let me not ask that. You can think about it if you want, that you cannot factorize. So when I say factorize and cannot factorize, I mean I want to factorize it so that these things, these coefficients are integers. Okay, otherwise, it's not much use in this context. It's not much use to factorize it so that you get irrationals and so on in this context. Okay. Yeah. So so we have this factorization. Now, how do we put it to use? So now how do we use this to say whether that number above is a prime or not? Yeah, so now we must try to use this factorizing this polynomial. How can we use this? So just think about it. Okay, I'll just drink some water. Yes. So can we use this factorization to factorize a number that we had initially? Yes, X can. So that's the idea. So similar idea we were doing yesterday. In fact, we had induction class, but we somehow ended up we were doing a little bit of number theory. That's the point, and that's the power of polynomials, right? This being true, this means that obviously it means that this polynomial is equal to product of these two polynomials as a polynomial, but it means that for any number x, both sides are equal, right? That is, we have proved all that, but simply that's what you should expect, and that's what happens, right? For any number x, both sides are equal. For any integer x, both sides are equal. And so you put x. I mean, that's the reason why we have factorized this polynomial. Otherwise, why would you? Right? So you can now see how polynomials are somehow subtle, right? Somehow they are being applied. I mean, they are kind of leading you to results in this kind of thing. Okay, you can contemplate over that, right? But you can see that it certainly is working out here. That it is you applicable. It's true for any x, and so you can put 57. So are we done? Do we need to say something more, or is it good enough to say that 57 to the power 4 plus 4 is not a prime? Yeah. But there is one small thing which is sometimes mostly is not needed, but I mean it's not so important to check, but you must check that none of the factors are equal to 1. Okay, and in a lot of arguments you do have to, it's not obvious. Obviously, in this case, it's obvious that this is not 1. And that one is not 1 is obviously this cannot be 1. But this is not equal to 1, you just check it. I mean, you just say that at least. Okay. So this is always the thing, right? Yeah, that when you, because I mean, you can factorize anything as a product of two things, even if it's a prime. But then you end up saying that one of them is 1. Okay. So sometimes you have to say, prove that something is a prime. Okay. If it's like that, then how do you prove that's a thing? You say, oh, okay, assume it's not a prime, so there is a times b, but then you do something and you show a is equal to 1. Right? And that's how you show something is a prime. Okay. But here, in order to say it's not a prime, again, you have to say that the factors are not 1 because, yeah, that's a simple thing in this case. But yeah, in general, you have to. So you can see how this polynomials are applicable in number theory. Okay. So, I mean, one can, in theory, factorize this number without knowing anything about polynomials. But then you see, just writing it as a polynomial somehow makes the job a little, it systemizes the thing, it systematizes the thing in sense, right? So yeah. Now, how about this? If we make this 100, yes. Yeah, and this is where polynomials are even more useful, right? You know what to consider of this. What is some standard some standard polynomial expression that is factorizable, and you try to reduce it to that. And this is again an idea that is repeatedly used in a lot of places. Okay. So, and again, you do the same thing. Okay. This is the idea that is used in a lot of places. So again, it's not a prime. No. Okay. So I would say that knowing polynomials, factorization of polynomials has helped us to solve this problem. If you ask me, that's what I would say. Just doing just numbers is not enough. Okay. So now let's move forward, but I think I'll just go a little slowly just to get you guys more used to this. How about if no, so it's the same thing, but how about if I say, um, is this a prime? Yeah, I just erased it twice. Sorry. Think. Yeah. Just doing more. I think I have done like less number of variations than I should do usually. I've sort of noticed that from checking the papers and so on, and by these interactions also. So I'm just trying to do that more. So this time, one of the students, just maybe someone with whom I was talking, they got into ISI this year. Yeah. So just happy for that. BStat, I think. He was in the senior, he was in the other batch. I am on this hotspot connection. And maybe we'll do a similar application, another kind of application thing today, where we will use polynomials in number theory, maybe remainder factor theorem in number theory. And please be on the lookout. I mean, if you see some Olympiads here and there, something happening, sign up for that and do, okay? You would have to find that, and I don't keep the updates with all that, okay? So, IOQM in India, other places wherever you guys are, yeah, means I know you where you are. So just see if there are some options, something happening, participate. That cannot be replicated in class. So you must participate as much as you can. A square plus B square. Okay, so how do you write it in that form? So you would say, yeah, there is, so sort of there is only one way to do it, right? That's what you're, yeah. Oh, no, no problem. Yeah. So this is 500 square. Mm-hmm. But then how do you factorize A square plus B square? Yeah, yes, right. So you can begin to do that. But how do we factorize it from here? Yeah. Ah, that is nice. You're saying you can write the 2ab itself as a whole. 2ab becomes a whole square. So yeah. So let's write a and b, and then so that all of us can see that whether it actually becomes or not. Let's see. So 57 to the power 50 plus b. So the b here is just this, right? Yeah. No problem. We should write it in the first time. Write everything and see. Yes, just for clarification, the a is this. Wonderful. Yeah, so it does become like that, right? 57 to the power 50. So not just that the powers are even, but because we have this extra 2, right? That is why it's working, otherwise it will not work. But yeah. So what is it that we should do next? Right. And this is, you got it. Good. So does everybody see, right? Just going with it, it just somehow it works in the end. Yeah, sometimes. That's what has happened here, right? You begin to write as the difference of difference of two squares is not always factorizable. But then you try to write it, and then it just turns out to be factorizable. Right? And so it does become a difference of two squares. It won't always happen, but you can see some things are setting in place, and so to the power 50 plus 2, whatever. This is doesn't the inside part doesn't matter too much. It's a square in the end that matters. This is a square. Difference of two squares. And again, you can fit difference of two squares. You can factorize. Okay. I mean, in general, what has happened is so the fact that this is a square and square is not really the thing. I'll maybe not go into too many details and say that what we just did is this basically. We did the same thing earlier, similar. Maybe I'll just say that what we did and now what you can do is to just factorize this. Yeah. Basically, yes. I mean, we have used that idea, right? That it is sort of that form. And so it's kind of, we did not use polynomial, but yeah, knowing that isolating that as A and that as B did help us, but either ways, yeah. Point is that you can factorize this. Yeah. And I'll not discuss it now because we have already done it actually in this question. And it's very similar to what we did earlier also. So you try to factorize this. This can always be factorized. This is the homework. It's easy. This is the complete version of Sophie Germain identity. If you is it called Sophie Germain? Yeah, right. So it should be that, and yeah. So that is good, right? Right. Okay. Now I want to go into another. Today maybe we'll just understanding factors is what we started with. We do understand some factorization, some factorization which we maybe did not know earlier. Okay. So that's one thing we did, and we saw its application in number theory. Let us just use something earlier we learned, like remainder factor theorem, maybe, to again apply it in number theory. Okay. The problem that we are interested in is again is very related to what we have done and things like we have done earlier. So, I mean, we have done this that a minus 1. So we know that any number a minus 1 would divide a to the n minus 1. Right? We know this fact, right? Basically, things like, 7 would divide 8 to the n minus 1. Yeah, 7 divided 8 to the n minus 1. Yeah, 7 is the 8 minus 1, right? We know these things. Now, okay, so without going too much into what and so on, what I am interested in kind of trying to do is something like this. Show, again, this is, we start with maybe how much time we have. Okay, so I just start with slightly harder versions. Okay, so we want to say that show in the sense that, yeah, show that 7 square does not divide, yeah, 7 square does not divide 8 to the 15 minus 1. 7 divides is okay, but I want to show that 7 square does not divide. Okay, so this problem is not very difficult, right? For those who know congruences, modular arithmetic, you can try using that. Okay, please do so, right? But the what we are going to do now is going to be more than just congruences. We are going to do something more. So you'll see. Okay? So this is going to be instructive, sort of not giving too much time to think about it, but do try it by congruences for those who know. Okay, congruences. Like 8 square is congruent to 8 square is 64. 64 is congruent to 15 modulo 79. Sorry, 49, right? And in this way, you calculate 8 to the 15 and you show it's not 1 modulo 49. And so you're done. But that is a very limited approach in some sense. So that you should try. But yeah, you should try that. But what I'm going to get into is this. What I'm going to say is that show that 7 does not divide 8 to the 15 minus 1 by 8 minus 1. This is the same question. Just removing, just canceling out 1 7 that is already there. Okay, just removing 1 7, that 8 minus 1 that is already there in 8 to the 15 minus 1. We know that. And now, so from the theory of polynomials or from geometry progressions or whatever, you know that that thing is nothing but this. Yeah, so we have done this. What we did, you would remember, is this, and you can bring the x minus 1 down. Okay, it won't be up. I mean, it's you can do that because it divides, really, right? Because there is a factor. So x to the n minus 1, right? So we have seen this factorization, or from geometry progression formula, you can say. This is what we already know. Can you, we already know that this is equal to this. Can you show that 7 does not divide this? Let us see. Yeah. So Satya and me, we did this yesterday, similar question yesterday. Today I want to do this slightly harder than what we did yesterday, maybe slightly. But the other people, we have done more number theory. So let's see if you can work this out. Show that 7 does not divide this. No, it could divide it as a sum, right? Think about that statement. That's not correct. It could divide the sum. That's not necessary. Yeah. Just try it. I'll just take a call. Otherwise, I will not be able to take it later. I'll sleep. sorry, I'm back. Yeah. So is it so Ishana, is that clear to you that I mean it could divide the sum if it doesn't divide? Two doesn't do, yeah, so that's, so it could divide the sum, but I mean that's, but it's a very interesting statement. I mean each of them is not divisible by 7, but each of them leaves remainder 1 when divided by 7. So you can use that because we, for those who've done number theory, we know that's the kind of thing adding, but we won't need that in general, but we'll see. Let's see. So, yeah, same thing, all of them same. Okay, so let's write it as a polynomial. Okay, okay, it's not correct to say that you can write this as a polynomial, but maybe you could say that you can consider the polynomial which resembles this situation, right? So I would write this polynomial. Okay, so this is a polynomial to consider. And then what? No, it doesn't. No, it doesn't divide x minus 1. No, how can this divide x minus 1? This is a big polynomial. Huh? We divide, yeah, we divide it by x minus 1 is the natural thing to do, right? Because x is a kind of the 8 is how what motivated. And so we consider when this is divided by x minus 1, and then what happens is the remainder. So, so can anybody tell me what will be the remainder if you divide this by x minus 1? In general, if you divide this polynomial by x minus 1, what's the remainder? 15, and it does not depend on the x. Obviously, it's going to be a constant. What do we learn from here? You can put x equal to anything. Put x equal to 8, and that's why we did this. Right? Put it equal to 8, and you get the remainder when it's divided by 7. Right? 8 minus 1, 7. Some number. Quotient is also a polynomial with integer coefficients, so we did not worry. So 15. Yeah, so 15 is a remainder, but that means that 1 is a remainder because, I mean, this is some numbers. I'm not interested in that. Maybe some m. Yeah. But again, obviously, we have to again further find the residue. And so 1 is the final residue because 1 is a number that's less than 7. And it's, you can write the whole thing as 7 times something. So 1 is the remainder. So the remainder is 1. Okay. So again, you see, polynomials somehow tend to be useful once again. Right? Yeah. But obviously, for those who know congruences, you know that like 8 is sort of 8 is congruent to 1 mod 7, right? So this leaves a remainder of 1. 8 square will also leave a remainder of 1. And so the total remainder will be the number of terms. And so it's 15 terms. So remainder is 15. And so the remainder 15 means remainder is 1. From there also you can say the remainder is 1 when it's divided by 7. Or you can say from this interesting sort of argument also. Okay. Okay. See this. And so we are done. So we know 7 does not divide it. Okay. But so first of all, is this clear? Then only I can move forward. Good. Nice. So this is a interesting thing, but you see, I mean, this is fine. This is fine. We got the remainder as 15, but this 15 is the important thing. Okay. The 15 is important. The remainder is 15. Where is the 15 coming from? It is this 15. If that was a n, the remainder would be n. Okay. If this was a n, the remainder would be n. So for any n that is coprime to 7, that is not a multiple of 7, the remainder would be something which is not equal to 0. The remainder would be that n, right? Which is not a multiple of 7. And so it will be a remainder, and then 7 will not divide it. So I'm saying that from our analysis, we can say so far that 7 does not divide 8 to the 500 minus 1 by 8 minus 1, because the remainder would be 500. It's not a multiple of 7. So what we learn is that this power is what gives everything away, right? If this power is 7 to begin with, then this will be divisible by 7. Again, by the analysis we have done, the remainder would be 7. Do you guys understand this point? Is it? Yeah. Because it is that power that gives you the remainder. Is everybody understanding that? Right? Yeah. It is this power which gives you the remainder. And so whether that power is a multiple of 7 or not will decide whether 7 square divides this expression or not, the original expression. Okay. So we know that 7 divides 8 to the n minus 1, and 7 square divides 8 to the n minus 1 if and only if 7 divides n. An extra 7 if you are looking for whether that multiple of 7 is there in it or not, that you have to ask that power. It's a surprising, interesting coincidence. Yeah, but it's true. And it's not so much of a coincidence because it seems to be a theorem. It doesn't even depend on the 8. It's sort of a minus 1. But let's not get into all the generalization. Should understand this first. Okay. That 7 divides that 8 minus 1, that base, 8 minus 1. That's fine. Now to know whether 7 square divides it, you would have to ask the power. Okay. So that's the nice thing. I'll leave it here. There are theorems which one can build on this, but I don't want to get to them. I think just this one small application and slight thing from yesterday. I did this, but I kind of did it more in a more easy way, sort of in a more, because it came from induction somehow. So you know, this okay, because other you guys know number theory. I've done it with you. So this is the result. Okay, so interesting. So all in all, we see that polynomials can be very, very useful. Okay, more applications can be seen if one tries to prove more stronger versions. How much? What is the largest power of 7 that divides this? That can also be can be shown that it is the largest power of 7 that divides n, which is a more quantitative version of this result, plus 1, because 8 minus 1 is already so. But we will not go into all that now. That will require good amount of induction and more comfortable. So yeah, let's leave this for today. And yeah, sorry, I'm not giving any homework. Set. Yeah. Okay. So let's meet for those who are meet on Tuesday. Okay. Yeah. Today Tuesday will do number theory. Okay. Satya, I mean, if you are in India, then you can also come on Tuesday's class, because I do plan to do a topic which will be connected. I mean, so that you will also be able to follow it in a way. So if you are, then you can join. Okay, it's up to you. Tuesday 9 p.m. Yeah. All right. So yeah, that's it then. Thank you.